Today we are going to talk about particulate matter monitoring, or PM monitoring, in session 3 of Quality Assurance Common Sense. We have people from Soldovia Village. We have Tracy Merrill and Michael Opheim, and they are there with equipment with their dust track devices in their van, ready to go out and place them for particulate matter monitoring. And we also have Chris Fish from the Alaska Native Tribal Health Consortium. And I want to first emphasize again, as with all of our courses, this is a strict zone of there is no such thing as a dumb question, because if there were, I would be asking a lot of them. Keep in mind that if you ask a question, you're probably doing somebody else on the line a favor, because chances are a lot of other people have similar questions. We're going to go over the National Ambient Air Quality Standards, which are abbreviated NAAQS, or sometimes people really get fancy and say NAAQS. We're going to talk about federal reference methods, abbreviated FRM, and federal equivalent methods, abbreviated FEM, and I'll mention their requirements. We don't have a lot of time to go into detail, but we're going to focus mostly on quality control for screening particulate matter methods. So using devices that are not federal reference or federal equivalent methods, devices such as Minie Balls or dust track devices that are used to get an idea of what the particulate matter concentration is in the air. We're going to talk about the different types of PM. This is a picture of a wood stove that produces a lot of PM10, and we'll talk about that. We'll talk about general quality control for particulate matter, and then, as always, I'm going to sneak in some data management and say again, write it down or else it didn't happen. You might as well just keep that in mind. If you can't prove that it happened with some piece of evidence, like a piece of paper, it might as well have not happened. That's the first rule of data management. Write down more than you think you will need, and legible scribbles are fine. Lots and lots of material admitted into court is handwritten. First of all, what is particulate matter? We're talking about two categories in general, and of course particulate matter exists in a whole range. You've got really big chunks in the air, but we're not worried about the larger particulate matter. Will get filtered out by the nose hairs in our nose, but what doesn't get filtered out gets into our lungs, and that's what causes people having to go to the doctor because they've got asthma, they've got breathing problems. So the two categories are called PM10, or particulate matter that is 10 microns and smaller. And so that includes this other category of PM2.5, which is particulate matter that's 4 times smaller than PM10. So PM10 includes PM2.5. PM2.5 is really small. So PM10 is produced by smoke, by dust, roads, and thank you, Wanda from Norvik, for providing these images. This is a picture of probably quite a bit of PM10 just at the surface here being blown up. PM10 is oftentimes blown by the wind, and it's generated from crushing, grinding rocks and soil, just like happens when you drive over it with a heavy vehicle. The finer particles that are 4 times smaller are produced most of the time by combustion, so something burning like the engines in vehicles that we tote ourselves around on. And it can include a lot of nasty stuff like toxic compounds, heavy metals. It's produced from automobile and other vehicle exhaust. Incomplete burning, so brush fires and forest fires where it's not burned at a high temperature, can produce PM2.5, and then of course some really nasty stuff in smelters. This is just an overview of the difference between the two, and you can do monitoring screening measurements for both. A lot of times people start off with screening measurements for PM10 because that of course includes PM2.5, and it's easier to measure PM10. So just looking at what these are, this is a human hair, this is beach sand, and then you can see that PM10 is about the size, just like maybe 5 side by side could fit in a human hair, so you could maybe just like barely see it. But then 4 times smaller than that was PM2.5. So you would have to place 20 PM2.5 particles side by side to span the width of a human hair. And I don't think we can see that with our eyes. And of course, the whole reason why PM2.5 is of interest is because the smaller the particle, the further deep into our lungs it can get. So, you know, we've all seen pictures of our lungs with all those little bronchioles, tubes. Well, the smaller particles can get in there, and then it takes a long time for our bodies to cough them out. How do you measure particulate matter? Basically, you pull air through a detector or filter. If you're using a device like a Minie Ball where you place a filter, what happens is you put the filter in the detector, you turn on the pump sucks air through the filter, so obviously any particulate matter that's in the air gets stuck on the filter, and then you package it up really carefully, making sure not to shake it and shake the stuff off of it, and then you ship it to a laboratory where they weigh it and they compare it to how much that very filter weighed when they sent it to you fresh. If you're using a detector, like a dust track kind of monitor, basically they work some variation of shining light through the pumped air. So the air is pumping through a chamber, and there is a light source and a light detector. And again, this is a simplification, but most of them work something like this. And then how much light gets through is proportional to the particulate matter in the air. And this is the same way smoke detectors work, except they use beta particles instead of light. Basically, the more particulate matter in the air, the less light will shine through. So they work basically from the point of view of pumping air through something where there's a detector, or it actually collects the particulate matter on a filter. All methods use air pumping, air moving through the device, so the flow rate is absolutely critical for particulate matter measurements. FRM stands for Federal Reference Method, and FEM stands for Federal Equivalent Method. And companies are always trying to get their devices onto this list, and EPA updates this list every 6 months or so. And there are hundreds of devices, and you have to use them really, really specifically in order to make what EPA calls attainment or non-attainment decisions. So in order to say that your air above your land doesn't meet, remember the NAAQS, the NAAQS, the National Ambient Air Quality Standards, you have to monitor for a full 3 years with complete quality control, and then provide that data to EPA, and then a decision can be made about whether your air is lower than the standard or higher than the standard. And that would be non-attainment. Your air does not attain the standard. So most people start off with screening measurements. So just to get an idea of what the concentrations are. And this is a picture of a Minie Ball. You can see there's different configurations of Minie Balls. This one looks a little bit different than the ones that I'll show you later. This is an older model. And a Minie Ball basically works just by pumping air through a filter, and then the filter is sent to a laboratory. Now, if you want to make measurements to compare against the National Ambient Air Quality Standards, then you must use an FRM or an FEM. This is written up in law, 40 Code of Federal Regulations 50.7. It has extensive QA requirements, but for PM10, it's not so hard. So a colleague of mine monitors for PM10 out at the White Mountain Apache tribe, which is about 4 hours east of me here in the White Mountains in Arizona. And he operates two continuous PM10, two PM10 monitors that are FEM, Federal Equivalent Methods, and he reports that data to EPA. And he's almost got a full 3 years of data, and his air so far looks like it is in attainment. PM2.5, because it's smaller, remember those particles, 4 of them will fit inside a PM10 particle in terms of just their size. PM2.5 is so small that it goes back and forth between being a solid and a gas. So the tricky thing about PM2.5 is that temperature is very, very critical. So the reason that there's really strict quality control requirements for PM 2.5 is because the temperature is important. Because if the filter gets hot, then some of those particles will turn back into gases, and of course then they won't be stuck on the filter anymore. So that's why PM 2.5 filters have to be shipped back and forth from the laboratory to you and then back to the laboratory in a cooler with blue ice. So QC requirements for PM 2.5 are a lot more strict than PM 10. This is a picture of FEM device monitoring particulate matter on the Navajo Nation, and you can see they're just barely at the limit of 33 feet from that temporary building there. And this is a picture of a TOM and a MET station. So you may have purposes other than comparing against the National Ambient Air Quality Standards. I mean, not to say that when your data comes in, you're not going to say, well, are we greater than 150 micrograms per cubic meter, which is the limit for PM10, but you can't take that data from a Minie Ball and say, all right, EPA, use this data and tell us whether we're in attainment or non-attainment. But you may want to start off with screening. So that's fine. If you have different goals, you don't have to use an FRM or FEM. But if you want to compare against the National Ambient Air Quality Standards in a legal way, then you can use either an FRM or an FEM. And the FRM methods are all filter-based, where you have to change a filter, and the FEM methods include continuous. So basically the two technologies are a TOM or a BAM, and these are two different types of continuous FEM monitors. But we're going to focus on screening type devices. These are pictures of Minie Balls, and we at the Tribal Air Monitoring Support Center have, I think, about 12 Minie Balls, and you can see they come in different models. This is the older kind, and now they come in these nicer cases, and this shows it closed, and it could be set up like this monitoring. They have batteries. The batteries run a pump. It really drains the batteries fast. This is basically the inside here, and you can see you've got a flow meter right here, one of those bubble type flow meters, and really critical that the flow rate be the flow rate that you want it to be, and that you monitor that as frequently as possible with any particulate matter monitoring. This is a dust track, and you can see again here it's in a case, and this is a picture from Seldovia Village, and then this is a little blow up of how it looks in the case, actually from the dust track manual. And then this is the device taken out of its case and put into this camo box that they used in Seldovia Village. So how would you use these screening type particulate matter devices? Well, you're going to use them to estimate the particulate matter concentrations. You could use them to find out if one place has a higher concentration than another. So in the Seldovia Village project, they monitored, remember, at 2 miles, like along Jackaloff Road, mile 2, and then another dust track on mile 4. So the difference between the concentrations at those two locations is very interesting to them. And then also to find out how concentrations change during events. So time of year, traffic during days when there's high traffic, events during days when people are burning a lot of waste. A lot of times people use portable screening particulate matter devices around forest fires all the time, at the perimeters of forest fires, at the perimeters of dumps, and near high traffic areas, to get an idea, just like they're doing in Seldovia Village, of what the actual PM concentrations are in the air. And if your concentrations are high, the data that you get, it doesn't mean that it's useless. It is very good data. The data that the Seldovia Village project gathered has all the QC. It's very well documented. The data can be used to justify spending more money to buy an FRM or an FEM that then can be used for attainment decisions. So again, keep in mind your end goal. You may want, if you find high concentrations, you want to make sure that all your QC is all in good shape. You did it, it's documented, and we need to ask EPA for more money so that we can purchase an FRM or an FEM. Going back to quality control. So quality control, the purpose of it is to estimate and limit your error. And remember, the error is the difference between your answer and the truth. And the truth being the true concentration of particulate matter in the whole air over your land. Well, obviously, we're only just taking a little bit of sample and we're sampling it through a filter. So right there, we know we're just taking a sample. We want this sample to be representative. Remember, we talked about that in the first webinar. So that's why you pick your location very, very well. But what are the components of error? First of all, you've got instrument imprecision. And the greatest factor for imprecision for particulate matter measurements is the wiggle or the slight variation in flow rate. You know the flow rate cannot possibly be constant. You know there's going to be breaks in the voltage at some point. You know, just slight wiggles will cause wiggles in flow rate. It could cause drifts in flow rate too. And that's the critical thing for PM is the flow rate. Instrument bias, slightly low or slightly high, a flow rate that's slightly low or slightly high could be caused by this drift since the last calibration, since the last time you said, okay, I'm going to make sure this is really running at 5 liters per minute. Now, if you're taking a filter and you're shipping it to a lab, the lab can make a huge contribution to error, right? So they have to weigh the filter. The scale at the lab doesn't work perfectly right on every single time. So they have a contribution to the error also. And then, of course, transporting the filter, it can get shaken. Temperature changes can cause errors. Again, remember for PM 2.5, if the temperature gets high inside that cooler, it sits somewhere for a long time and all the blue ice just turns into gel and it gets hot in there. Some of the PM 2.5 on the filter may turn back into a gas, and then when the lab opens it up and weighs it, it's going to weigh less than if that filter had been shipped in a really cold cooler where all the particles stayed on the filter. So, precision. Just looking at precision error, you can never totally eliminate precision error. And the definition of precision error is it's wiggle. It's sometimes up, it's sometimes down. It's often called the random component of error, as opposed to bias, which is the systematic component of error, where it's systematically high or systematically low. Precision is the random component. It's estimated by measuring what you want to be the same thing over and over again to see the wiggle. So this is just a picture of a scale, and you know from reading any scale like this, it could be 5 liters per minute, right? But sometimes it's going to be a little low and sometimes it's going to be a little high. Sometimes it's a question of how well can you read that little needle. Sometimes that's a contribution to error too, like if you're looking at it at a different angle. And that brings up procedures. That is why it's really important to try to do the same thing the same way every time, because you don't necessarily know that just because you're looking at it right on every time, that's actually minimizing your precision. And then somebody else comes and they hold it down like they're wearing bifocals or something, and they hold it down. Well, then it looks different to them. They're going to say it's, like when you're looking at your speedometer and to the passenger, it looks like you're going 95 miles an hour, but the driver says, no, I'm only going 65 because you're looking at it from a different angle. Well, that's why precision is minimized by following procedures. There's 2 sources of precision error. There's what happens in the field, and this could also mean you're just sampling this proportion of air, right? There's all this other air out here. We try to make our sample really representative of like the whole air around Road 2 by Jackaloff Road by carefully placing our sampler in the middle, and we hope it's representative of everywhere. And then there's the lab. You could be like this guy, like I am in a lab, constantly spilling everything. So the lab has a contribution to precision error also. Just so that you guys know what happens in the lab, what they do is they take a filter, and they have standard filters that they weigh over and over again. And they have little tiny standard weights that they put on the scale. And over here you can see this is Robert Mosley, who works in the Tribal Air Monitoring Support Center. And you can see he's got a little area here that's caged off, and he's got the filters sitting in there. And he has standard filters and standard weights, and he weighs them. And they're supposed to agree. Every time he weighs the same weight over and over again, it has to agree within plus or minus something. And if it isn't, then he knows that all the filters he weighed in that batch are suspect, and he needs to figure out what the problem was, fix it, and then weigh them again. Let's talk about what you guys have to do to estimate the precision error of flow rate for a Minie Ball. So the way Minie Balls work is they're supposed to always sample at 5 liters per minute. So if you start sampling on day 1 and it's reading 5 liters per minute, that's great. You put the filter in, you let it go for 24 hours, you come back the next day, and you take the filter out and you measure the flow rate again, and now it's 6 liters per minute. Well, you know the target flow rate is 5 liters per minute. So you know, wait a second, it has to be 5 liters per minute. So at this point, you recalibrate it and set it up for 5 liters per minute so you're ready for the next filter. But you log your results. So here's just a little table that shows the measured liters per minute the first time, the target liters per minute, and that's 5 all the time, the difference between the measured and the target, which is 0, the relative percent difference between the two, which is just the difference divided by the target, and that's 0, of course, if they're both 5. And then after sampling, it was 6 liters per minute. So now it's 6, what you measure, what the Minie Ball shows on its little bubble meter is 6 liters per minute. The target is 5. The difference is 1. 1 divided by 5 is 0.2. You can already estimate your precision error of the flow rate alone based on this. The average of these two is 0.1, which is 10%. So this is just an illustration of how the flow rate and little variations in the flow rate are really important. This project has just started, and that's fine. A precision of 10%, you're probably never going to get too much better than that. I mean, a lot of times 15, 20% imprecision would be good. Just to remember, 0.05 is 5%, 0.10 is 10%. Some precision is unavoidable, but you minimize instrument imprecision by keeping the flow rate steady at whatever the target is. You minimize other imprecision by following the procedures the same way every time, and let's hope the lab does that also. And you minimize anything that could happen during transport by carefully handling your filters and doing the same thing the same way every time. So how do we know that the flow rate is 5 liters per minute? That's what the Minie Ball says, right? Its little bubble meter says 5 liters per minute. But how do we know that thing just isn't stuck at 5 liters per minute? Or we turn it on, anything going through there shows 5 liters per minute. It says 5 liters per minute, we change the flow rate and it goes up. But is it really 5? What if it's 10 and it's just sitting on the 5 line? Well, we know because it has to have some sort of external calibration. So devices are shipped to you calibrated if you buy them from the manufacturer, but then stuff happens over time. They have to be periodically recalibrated. In this case, the dust track was calibrated by Chris Fish at ANTHC, and what he used was something like this. This is a handheld external flow rate transfer standard, and sometimes they're abbreviated FTS, flow rate transfer standard. And what this is you stick this white thing over the inlet and it measures the flow rate itself. So your device will be showing the flow rate, and then you stick this on there and it'll be showing the flow rate too. And your goal is that these two say the exact same thing. Because your device could drift, and you could see that this is a transfer standard. You can see it's got a nice EPA sticker. We have some of these at the Tribal Air Monitoring Support Center that we loan out to tribes when theirs are sent back to the manufacturer for recalibration. Ideally, Such a flow rate transfer standard is used during the project and again at the end, but at least once. It's important to get some double checking of the sampler's flow rate. So this again is called a flow rate transfer standard. A lot of times I call it a handheld because your device has a flow rate detector in it also, but this is an external one. It's like a double check. So the conclusions about precision. Well, first of all, why is flow rate so critical? It's because the particle size that gets to the filter or the detector depends on the flow rate being exact. So the particle size, now how that works, for example, in the dust track, well, in a lot of devices, they have what's called an impactor plate. Sometimes they have a cyclone. But what happens is air comes through, and then there's this impactor plate. The heavier stuff, like stuff that's bigger than PM10 in this case, it continues on because it's heavy. So it can't make this turn. So PM10 and smaller go because they're just light and they go with the air. But the heavier stuff bangs onto this impactor plate and then it doesn't make it through to the detector. But obviously the flow is really, really important to make sure that that cutoff of size, the particles that get stuck on the plate and don't make it into the detector or onto the filter, that depends on the flow rate. So the particle size is affected by the flow rate. And the device is designed so if you've got a PM 2.5 inlet, it has to have the flow rate exactly right, what the manufacturer's intended and designed it, so that only PM 2.5 makes it around the corner to your filter. And then the amount of particulate matter that gets to the filter or the detector is directly proportional to the flow rate. Proportional means that if the flow rate doubles, then the particulate matter collected is also doubled. So, if you think you're sampling at 5 liters per minute, but you're really sampling at 10 liters per minute, then you're going to get twice as much PM, not thinking about the particle size, but just twice as much PM on that filter than if you really were sampling at 5 liters per minute. So the flow rate is really, really, really critical. Okay, bias. Remember, bias is a consistent jump, either always high or always low. So that would be, in this case, we're talking about flow rate. If the flow rate is always high, then there's always going to be a little bit more particulate matter on the filter. Bias could also happen as a result of a transport problem. So if you somehow just move your elbow in a certain way and you knock particulate matter off the filter, and if you always handle it like that, sliding it into its little baggie a certain way or something, would that cause a high bias or a low bias? Probably a low bias, right? Because you'd be knocking some of the particulate matter off of the filter. Or could a lab problem cause bias error? If they have dust on their scale and they don't tear their scale before they start, would that cause a high bias or a low bias? In general, it'll probably show that there's more particulate matter on the filter than there really is, just because they've already got dust on their scale. So these are potential sources of bias error. Again, it's a consistent jump, always high or always low, and you really want to minimize bias. So how do you do that? A consistent flow rate at the target flow rate, so that's whatever the instrument manual says is the target flow rate, is critical. They work by separating particles of different sizes based on how they act at that target flow rate. Sometimes the inlet is called a separator. You carefully follow chain of custody packaging and shipping, and we have a folder on the website where you can click and see different examples of chain of custody documentation. You write everything down. Some change that you made could cause a problem, and you might not realize it at the time. But you can go back and look at your logbook to see what changed at that time. If, for example, you see all of a sudden a jump in your particulate matter results coming back from your lab, you could go back and look at your logbook and see around that time when that change happened, what changed. And the only source you have for that are the detailed notes that you keep in your logbook.